Remember the days when landline phones were the pinnacle of communication technology? We have since witnessed an incredible evolution to mobile phones and then to smartphones, each leap bringing revolutionary changes and changing the way of life itself. The evolution of quantum hardware has involved numerous groundbreaking technologies, each contributing uniquely to the advancement of quantum computing. The journey of quantum computing hardware has been a remarkable one, tracing back to the early theoretical foundations laid in the 1980s and 1990s. From those nascent days when the concept of qubits was first proposed to the sophisticated quantum processors we have today, the field has seen tremendous progress. The evolution of quantum hardware has involved numerous groundbreaking technologies, each contributing uniquely to the advancement of quantum computing. First, let's delve into superconducting qubits, one of the most widely adopted technologies in the field of quantum computing. Superconducting qubits rely on superconducting circuits cooled to extremely low temperatures to exploit quantum effects. We need this technology because superconducting qubits are easy to fabricate with the current semiconductor fabrication processes. This helps us to achieve long-term scalability and efficient integration with other integrated circuit platforms. Superconducting qubits can be controlled using microwave pulses, making them compatible with existing semiconductor fabrication techniques. Active research in this direction has enabled better coherence of qubits and faster gate operations, and they are gradually improving daily. Companies like IBM, Google, IQM, OQC, and Rigetti are leading the way in developing superconducting quantum processors with the aim of building scalable and fault-tolerant quantum computers. Transitioning from superconducting qubits, we move to trapped ions, another promising approach to quantum computing. Trapped ions use individual ions held in place by electromagnetic fields to encode quantum information. Laser beams manipulate the ions' quantum states, allowing for high fidelity operations and longer coherence times. Companies such as IonQ, Quantinuum are making significant strides in trapped ion technology, aiming to build robust and scalable quantum computers with high levels of precision and control. Next, we explore photonic quantum computing, which leverages photons, an elementary particle that is a discrete agglomeration of electromagnetic energy used to encode and process quantum information. Photonic qubits can travel long distances without losing coherence, making them ideal for quantum communication and networking applications. Companies like Xanadu, Quandela, and Psi Quantum are exploring photonic quantum computing, aiming to develop quantum processors capable of performing complex calculations and secure communication protocols. Furthermore, there is the concept of topological quantum computing, which relies on exotic particles called anyons to store and manipulate quantum information. Anyons exhibit non trivial braiding properties, making them highly resistant to errors caused by noise and decoherence. Microsoft is leading the charge in topological quantum computing with its development of topological qubits, aiming to build fault tolerant quantum computers based on robust topological properties. Lastly, we have analog quantum computing, an alternative approach that focuses on evolving a quantum system over time to find an optimal solution to a problem rather than performing general purpose computation. Analog quantum computers such as quantum annealers or analog quantum simulators works by gradual time evolution of a simple Hamiltonian to a final Hamiltonian that encodes the optimal solution of the problem while maintaining the ground state throughout the process. D-wave systems pioneered the field of quantum annealing with its D-wave quantum processors, which are well suited for optimization and sampling problems in various fields, including finance, logistics, and material science. Quantum computers require specialized hardware components like the quantum data plane, control processor plane, and host processor. These components form the backbone of a quantum computer, managing qubit states and processing quantum information. Customized integrated circuits and quantum system on chips QSOCs are essential for integrating and controlling quantum operations at scale. The quantum data plane includes the physical qubits and the circuits that manipulate them. This is where the qubits reside and the quantum computations occur. The control processor connects with the quantum data plane to manage and execute quantum operations by translating high-level quantum algorithms to low-level control signals. These signals manipulate the qubits. The host processor is the classical computer that manages the overall operations of the quantum computer, such as running the algorithm, resource management, and data processing. Custom integrated circuits or custom ICs are tailored specifically for quantum computing to carry out the operations of control and measurement of the qubits. Some of the components described before can also be embedded into a single chip called the QSOC. It can integrate control electronics, qubits, and readouts in a single chip, and it is suitable for the scalability of the quantum systems. Now, by simple observation, you can see that classical computing hardware only consists of one type of technology, that is CMOS, complementary metal oxide semiconductor based on silicon technology. However, for quantum hardware, since it is in the early stages, there are different hardware platforms in order to explore their performance in certain applications and decide upon the most efficient and performant platform. Additionally, classical computers do not use quantum mechanical properties, which means it cannot perform parallel operations inherently. But quantum hardware uses inherent parallelism and using the laws of quantum mechanics to enable quantum parallelism operations. Quantum computers can become the laptops and desktops of tomorrow, but it is important to emphasize that they will not replace the classical computers. There is active research being done on QSOC and cryogenic CMOS chips that will potentially enable desktop or laptop based quantum computers, but they will be used for specialized applications. In conclusion, the landscape of quantum hardware is diverse and rapidly evolving, with each technology offering unique advantages and challenges. The pursuit of building practical and scalable quantum computers is driving innovation and collaboration across the academia and the industry. Thank you so much.